Hello, I'm Ron Espiritu and I work with the members on screen to complete the final design assignment of the semester. The task of this assignment is to maximize a piezoelectric thermal cantilever tip displacement. The system has this geometry where there's a metal wrapped around a piezoelectric. This metal can be defined into three distinct regions, a top side, a right side, and a bottom side. We're free to decide if each region is either gold, titanium, or chromium, and the overall dimensions of the system and the geometry are free to be decided as well. We're free to choose between a rectangular cantilever setup or these two trapezoidal setups. There is a 1 volt voltage difference applied between these two fixed boundaries, and the temperature on these regions, as well as their position, are fixed as well. We're constrained in the length, the width, the max thickness, and the mass, and the different regions are constrained to each other as seen on screen. I mainly focus on the building of the Flex PDE simulation. It's important to understand how the system functions to create thermal and piezoelectric strain. By applying a voltage difference, a current is created which induces a voltage across the piezoelectric and also creates heat within the system. This creates a piezoelectric strain and a temperature change which causes thermal strain. It's also vital to understand the different PDEs used to set up the equation. The first being a form of Gauss's law, which allows us to solve for the free charge everywhere. It calculates it from the electric field density, which is calculated from the piezoelectric constitutive equation. The second equation explains that there is no active flow of current in or out of our system. It's calculated using the current density form of Ohm's law and the property of an electric field that it's always pointing in the direction of the fastest voltage decrease. This equation allows us to solve for the voltage everywhere within our system. The third equation is a derivation of the heat equation stemming from the assumption that temperature doesn't change in time. It states that the internal heat generation is equivalent to the rate of change of temperature in space. The internal heat generation is calculated from the dot product of the current density and the electric field, which is equal to the electromagnetic energy per unit area, or the flow of it rather. The final equation comes from the stress form of Newton's second law. In setting this partial differential to 0, the x and the y displacement that puts the system into equilibrium is calculated. It's built by calculating the piezoelectric strain, which is the D matrix multiplied by the electric field, and the thermal strain, which is the thermal coefficient multiplied by the change in temperature. This is related back to the equation by multiplying these strains by the material's stiffness. Flex was built in 2D by first building the geometries. From there, all the previously stated equations were implemented, and the material parameters for each region were added. From here, several test cases were performed to verify our model. Test case 1. So if built correctly, the model should have the same charge in the top regions as the bottom region, but with opposite signs. This is a property of capacitors, which holds true in our system. Test case 2, here we're testing the voltage distribution. With no voltage, all the contours should be uniform, which they are. And with a voltage, there should be a non-uniform distribution, which there is. In test case 3, we're manipulating geometry. It's predicted that removing the side metal causes temperature to be uniform, and for the system to mimic a capacitor, since removing the side piece breaks the circuit, removing all current. And this is true for our system. Also, dropping the length of the metal was predicted to force our system into a side metal dominated strain, since it would be the largest region, which is true as well. Test case 4 tests the electrical resistivity and the thermal conductivity. As previously stated, under a no voltage difference, we have uniform distribution. Under a voltage difference, we have a distribution that is non-uniform. We test under a high thermal conductivity, which produces a lower temperature as expected. And we test under a high electrical resistivity, which produces a lower temperature as expected due to a lower current. From here, it could be predicted that our optimal solution will have a thin piezoelectric to maximize field, a triangular geometry, a high top thermal expansion, and a high bottom stiffness. To optimize material choices, the effect of every parameter in every region was tested. It was determined that it was best to have gold on top, titanium on the side, and chromium on the bottom. To optimize geometry, the 3 geometries were tested. It was discovered that the rectangular geometry produces the best curvature. And the best thickness ratio was calculated by testing each case. And it was found that a higher metal to piezoelectric thickness was ideal. So scripting was done to determine the best material dimensions. We use the get displacement function to find the max displacement after a flex iteration, the mass underscore c, which finds the mass of a system given the materials and its size, and the grad function, which finds the gradient using the numerical methods. From here, grid search and gradient descent were performed to find the ideal dimensions. It was discovered that the ideal length of the cantilever is 0.9 millimeters, and the ideal thickness is 0.05 millimeters, both values at the extremas of their respective ranges. The high length can be justified by there being a higher bending moment for higher lengths, and the high piezoelectric thickness can be justified by the desire for there to be a lower piezoelectric shrinking. This indicates that the thermal expansion heavily dominates the system's behavior. Also, the rectangular region is justified because this maximizes the amount of thermal strain occurring within our system.